Okay, so in this system, I have two objects. I have object A and object B. So they may have their own masses, they can move in different ways, they are completely separate objects. However, the system is everything together. So it's object A connected to object B by the spring. So as a system, we kind of treat it as one, okay? So according to the law of conservation of momentum, what happens to the momentum of the system? So the momentum before a collision is equal to the momentum after a collision. Okay, so the momentums of object A and B are going to change when the spring is released, but why won't the momentum of the system change, right? Well, that's because of the law of conservation of momentum. When we talk about the system, whatever this system is, right, the momentum before has to equal the momentum after. Okay, so the system is everything. So A, right, so both of these start at rest, and A is going to move to the left, and B is going to move to the right. So what's going to happen is they're going to have equal and opposites. So in this case, here's what's happening. Beforehand, right, so the momentum before equals 0 because both objects are at rest. Okay. Now, when they start moving, what's going to happen is the momentum after is also going to equal 0 because the momentum of the objects will be equal and opposite. So the momentum of object A, right, is going to be equal to the momentum of object B, but they'll be going in opposite directions. So one of them is going to be negative. Since we have A here, right, then it's going to be, since A is going to the left, if the left is the negative direction, it'll be like negative this and a positive that. So when you add them together, it equals 0. Okay, so if we add these two together, we'll put this equals 0. So that would be after. For 9, we're going to explain the difference between elastic and inelastic. And for 10, we're going to use the law of conservation of momentum to determine the final velocity of a system after the collision. So to explain the difference between elastic, for elastic, the collision bounces, and for inelastic, the collision sticks. So for an example of an elastic collision, that would be like the bowling ball hitting a pin. It hits the pin, but they don't stick together. They just keep going, right? So they bounce off of each other. For an inelastic collision, this one this one could be a football player tackling another player to the ground without letting go of him. Right? So he's not just running into them and they're bouncing off of each other, which a football player can tackle that way, but this is where he comes and he grabs the guy, falls to the ground. Okay, that would be an inelastic collision where they'd stick together. So the goal for the conservation of momentum problems, you want to make sure you're drawing the picture, that you're writing an equation for each picture, and that you're using that to solve for the before and after situation. So here's what we have. We have a girl standing on an unmoving skateboard and someone throws her backpack at a velocity of 4 meters per second. What speed will she go together? Okay, so we have a girl on a skateboard. And she tells somebody to throw her backpack at her. So then we have this backpack in the air. Now the person throwing the backpack doesn't matter. That's not part of the system because I'm really bad here. Backpack, just so you know, this is her backpack. Okay, we don't need to worry about the person throwing because the mass of the person throwing is not going to end up being part of this system. That person's not colliding with the girl. They're just throwing the backpack. So the backpack's moving. The girl is at rest. All right, and then afterward, what's going to happen is this girl now has her backpack, right? Now she's holding her backpack. Okay, so there's only one picture here. So each picture gets its own momentum equation. So we have mass times velocity. Now this is the before, so it's plus mass times velocity equals mass times velocity. So what we need to do is each picture we need to look and determine its mass. So here it's just the backpack. So I take a look and just the backpack is 10 kilograms. Okay. For here the mass is the mass of the girl with her skateboard. Since they only say 40 kilograms, we're going to assume that the skateboard is included in that weight. So that's 40 kilograms. Over here, however, notice I have the mass of the skateboard and the backpack, which means I need the total mass. So if we put the girl with the backpack and the skateboard onto a scale, right, then the mass is going to be the sum. So that's going to be 10 kilograms plus 40 kilograms. This is the total mass. So the total mass is 50 kilograms. So now let's go back and look at the speeds. So everything is mass times velocity. Well, the velocity of the backpack is 4 meters per second. All right, now I can add a plus here because I'm adding the before collision. I'm adding everything that has momentum. Well, the girl is at rest, so she's at 0 meters per second. And then we don't know the velocity together. That's what we want to know. What is the speed the girl will go on the skateboard here? So we don't know that one. All right. So we have 40 plus 0 equals 50 times velocity. And so we want to divide both sides by 50. And then the new velocity is 0.8 meters per second. So here's the thing. The backpack was going 4 meters per second, but now it's only going 0.8 meters per second. So the backpack lost tons of momentum. However, the girl, she was going 0, and now she's going 0.8. So she has gained momentum because she has gained speed. So she's now going faster. So what direction will the girl move after she catches her backpack? Since this is a positive number, we are assuming she's moving to the right. To the right. So last question here. We have a bowling ball is thrown toward a bowling pin. Okay. And then this is the before. And then after it hits and the bowling pin goes flying. Yes, I know my pictures are not ideal. We'll just have to we'll put a couple holes here. Right? Okay. So I have all my pictures, so I need to find mass times velocity, mass times velocity. Now this time, these bounce. They do not stick together, so I actually have two separate pictures. So I have to find the mass times velocity 4 different times here. So for the bowling ball, the mass is 7.5 kilograms. For the pin, it's 2.5 kilograms. And now what I need to do is find all the velocities. So before the collision, all right, so before the collision, the bowling ball is going at 9 meters per second. And if you play bowling, you know that the pin is at rest. Okay, so this is before. All right, so now I'm going to look at after what happens here. After the collision, the pin flies away with a velocity of 11 meters per second. And the velocity of the bowling ball after the collision is what we're looking for. So I'm just going to put a V. You can put a V prime there, like I'll do that, because before it was 9. V prime is the velocity after. Because this is our only unknown, though, you're okay if you don't do that. So this is what's happening after. So the total momentum after has to be the same. So I need to put a plus sign in between the two pictures. Okay, so now we want to do some calculator work. 7.5 times 9 is 67.5 plus 0 equals 7.5 V, and then the new velocity of the bowling ball, plus 2.5 times 11. Okay, then what we need to do is subtract 27.5 from both sides because we're trying to isolate the variable term. We have to get rid of the non-variable term on the same side. So then we get 40 equals 7.5 V prime. Divide both sides by 7.5 to get that V by itself. And then the new velocity of the bowling ball is 5.3 meters per second. Okay, what direction will the ball go after the pin? This is a positive velocity, so it's going to go in, it's going to go to the right because we're going to just assume positive velocity is to the right. What direction will the pin go after the ball hits? Notice the pin also has a positive velocity, so it is going to also go to the right. Okay. Now you could have changed direction. You could have said, you know, up is positive, right? Or away from you is positive. So what the big idea you need to know here is since both the velocities are positive, they're going in the same direction.